Today I'm going to discuss the topic of random walk, with the question of whether random walk will return to the origin after it has started. Let's first understand what a random walk is. A random walk, starting from the origin, walk in a random direction. If we're on a line, the only directions we can walk is left and right. Then we choose to walk in either direction. After we walk in that direction, we can choose to walk in a random direction from that position again. Then we can walk again in a random direction, and we can choose a random direction to walk again. This process continues, forming what is called a random walk. Let us investigate the behavior of random walk further. Now, we denote the displacement after we walk in n number of steps r sub n from the origin. This is n steps after random walk. This is represented displacement factor of the position of n steps after a random walk. Then, using this notation, we can construct the following: r sub n and r sub n plus 1. That means the displacement of our position after n steps and the displacement of our position after n plus 1 steps of random walk. We denote that difference by T sub n. T sub n represents this difference factor between the two factors r sub n and r sub n plus 1, which we can describe by this relationship. Using this relationship, we can then take the expected value of both sides. And by the linearity of expected value, we can split the expected value into its constituent parts. Then we can square both sides. After we square both sides, we can distribute according to the distributive law. Then we analyze the term on the left-hand side. This is the r sub n term, and this is the t sub n term. Each term can be either positive or negative. If they are alternating sign, then the product will be negative. But if their signs are the same, then the product will be positive. Here we can see we have both positive and negative cases. That means the average cases we expect to get is just 0. Therefore, the product on the left hand side have an expected value of 0. That means we can just ignore the term on the left hand side. Just focusing on the term on the right hand side, we have this relationship. And remember that T sub n is the difference between the R sub n factor and the R sub n plus 1 factor. And let each step that we walk in a random walk be just 1 unit away from where it is before. That means the magnitude of the T sub n factor is just 1. Therefore, looking at the expected value of T sub n, we can just replace that by 1. Then the other stays the same. So we have found a relationship between R sub n plus 1 and R sub n. But we want to find a relationship of R sub n alone. How can we find that? We can just start by looking at R sub 1. R sub 1 is just a factor 1 unit away from the origin in either direction. So the expected value of R sub 1 is just 1. Then we square both sides. And we add 1 square to both sides. Then we created the same form as the above. Since this form is same as this form, so we can replace the left hand side by the next R sub 2 square, and the right hand side is just equal to 2. Then we can add 1 square to both sides again, and we created the same form again. So we can replace the left hand side by R sub 3 square, and the right hand side evaluated to 3. Then this process continues. Until we get to R sub n, which, as you can find by recognizing the pattern, just R sub 3 is equal to 3. R sub 3 square is equal to 3. Therefore, R sub n square should be equal to n. n by square root both sides, we find that r sub n should be equal to the square root of n. What this relationship tells us is that after n steps, the expected displacement away from the origin should be about square root n units away. That means if we have taken n steps of random walk, we are expected to find ourselves square root n units away from the origin. Or you may need to take n square steps to reach n units away from the origin. But this also suggests a probability of, if this is the origin and we can plot and the right hand side is just n units away, then the square root of n should be right below the halfway point in most cases. Therefore, in most cases, we expected to end up more likely at the square root of n rather than the halfway point after taking n steps of random walk. And due to this difference in the probability, maybe we guess we can approximate or we can guess the probability distribution should decrease over the distance. As we get further away from the origin, the probability of getting there will decrease. So this is just our guess. Let's try to verify it by evaluating the probability of getting any position away from the origin. Let's say we are at I units away from the origin, and we have already taken n steps of random walk. What is the probability of ending at I units away from the origin after taking n steps of random walk? If we just break the vector or displacement of I into individual displacement vector like this, then we can say that the overall vector of n over n steps should add to the vector of I units away from the origin. Then what about the remaining positions? They should cancel each other out due to the vector sum. So if we have taken n steps and we just end up at some I units away from the origin, then if we count up the total number of the right arrows plus the total number of the left arrows, since we have just taken n steps, then those number of arrows should add up to n. But the factor sum or the net sum, since the opposite arrow have the exact opposite direction, therefore we can associate it with a negative sign in front to denote the factor sum in opposite direction. And this just is I units away from the origin. So they sum to I. And with these two relationships, we can add them together. If we just add them together, we get the middle terms cancel. But we can also subtract the bottom from the top. And we also get this relation. And from both relationships, we can find the number of right arrow and the left arrows to be these two expressions. And with the number of arrows in both directions now known, we can find the probability of ending at I units away from the origin. If we just count up all the possible ways of ending up I units away from the origin, after taking n steps, since we know how much of each arrow we have this much and this much, and we know that these arrows are just displacement factors, and the factors just sum together, and the factor sum has a property of they don't matter the order that they sum. Therefore, even if we just associate the factor randomly, as long as each one got a position, then the total sum of those factors should just all be equal to the factor I units away from the origin. And this is what we need to count. We need to count all the possible arrangements of all these arrows or factors that sum to a factor displacement factor of I units away from the origin. And how can we count that? Since there are a total of n positions, we can just choose n position, and out of those n positions, we can just choose the number of right arrow or the number of left arrow to place, and we choose how many ways we can place the number of right arrow or left arrows into the position of n units. So how can this arrow distribute in these n positions? And since after we have put down one type of arrow, either left or right, then the remaining arrow will just be another type, either left or right arrow remaining. Therefore, either way, if we just count the left arrow first or the right arrow first, it doesn't matter. Therefore, these two values should be the same. So we just count the possible arrangements of these right and left arrows along the n positions that they can be in order to sum up to a displacement factor of I units away from the origin. Now we just need to count what are all the possible ways of doing that. That means all the possible ways that we can place the factor or arrows in along n positions. Since each position we can have two choices, either going left or going right, then along the n positions we just have 2 to the nth power choices as the total number of choices, and that is the denominator of our probability. So this fashion of n choose n number of right arrow or n choose n number of left arrow over 2 to the n should be equal to each other. And remember that we have just found what the number of right arrow and left arrow should be. So we can just substitute the value in. And either one is okay since they are both equal in value, and both are just representing the probability of n at I units away from the origin. After taken n steps, and this is the probability that we want to find. So now we know the probability of ending up any units away from the origin. Now let's just plot to see what that probability distribution looks like. And this is what it looks like. It looks very similar to a bell curve, isn't it? And it just has the above equation describing it. with n is the number of steps that you have taken in a random walk, and I is the position that you end at. And this is the probability density function that the above equation describes. And with this probability distribution found, we can finally address our question from the beginning, which is how likely are we to return back to the origin after we have started a random walk, and with the origin just in the middle, and we have just found out the probability of ending at any u displacements away from the origin. And the question that we ask is, how likely are we to end up back at the origin? That means 0 units away from the origin. Therefore, it is just equivalent to I equals to 0, and we can just substitute 0 into I into the above equation to find out the probability of ending at the origin after n steps of random walk. But we also want to know how often a random walk will return to the origin, and then we can consider the expected value of returning to the origin after some number of steps. And we can find that expected return to the origin to be the expected number of return to the origin after if we think about how many steps it takes to return to the origin, we may take some steps to some direction, and then this is away from the origin, and then if we want to return back to the origin, we need to take the same number of steps as we take away from the origin. So these two number of steps should be equal. If we take n number of steps away from the origin, we will need to take n steps back to the origin. So the total number of steps is just 2n. 2n is just representing any even number. So we return to the origin after an even number of steps, represented by 2n. And we can find the expected number of steps to return to the origin. Expected number of return to the origin after an even number of steps by multiplying the probability of returning to the origin after 2n steps by the contribution of to the number of returns to the origin, and each step has a contribution of to the number of return to the origin is just 1. They just contribute 1 return to the origin, and we want to find out the expected number of return to the origin after 2n steps. Now, since this is just 1 return, and we know the value to be 1, and what we want to find is just what is the probability of return to the origin after an even number of steps. And remember our formula derived from before. Remember this. This just represents our probability of returning to the origin if we sub I to be 0 after any number of steps. So we are interested in the case of returning to the origin after 2n steps, and we just substitute 2n into n and 2n minus 0, since we are returning to the origin, divided by 2 all over 2 to the 2n, and this just simplifies to 2n choose n, all divided by 2 to the 2n. And this is what we want to find. But of course, we need to sum across all the possible n values to find the total expectation of the number of return to the origin after 2n steps. So now, in order to find the expected number of return to the origin after 2n steps, we just need to find what is this sum equal to. What is this sum equal to? First step, we evaluate this sum by just expressing the choose function using factorials in this way. Then we can expand the factorials to express what they really mean. which is the product of 1 to 2n divided by the product of 1 to n squared, all divided by the 2 to the 2n. Then we realize that these cancel each other out. Then what we end up with is just n plus 1 to the 2n, the product, all over the product of 1 to n, all divided by 2 to the 2n. Then we may write it in a different way, like in this way. So that we can just denote that we can denote this term by p sub n, and we realize that this sum is just a sum over this sequence with this journal term. So p sub n is the journal term of this sequence, and we just summing p sub 1 to p sub n, and then up to infinity. This is the sum that we want to find. But it may be useful to find out what p sub n plus 1 is, so that we get a sense of how fast one term is increasing or decreasing to the next term. So one way to do that is to find out the ratio between the journal term of the next term p sub n plus 1 over the journal term p sub n, and we have the expression on the right. With that we can just substitute in. So we can just substitute in 2 to the 2n plus 1, and n plus 1 is just n plus 2, and all to the product of 2 to the n plus 1, 1 to the n plus 1. This is the general term for the p sub n plus 1. And then we can just write out the general term for p sub n as this. Then we can simplify or expanding the 2n plus 2 and the n plus 2 and the 2n plus 2 and 1 and the remaining stays the same. Now we can expand the product or write out more of the product on the top to see what is really the pattern. So n plus 2, then going to 2n, then 2n plus 1, 2n plus 2, all divided by 1 to the n times the n plus 1, 1 divided by 2 to the 2n, n plus 1, 2n, and then we can cancel out common terms, like these two common terms, and now here should be n plus 2. Now n plus 2 to 2n common terms, and what we are left, and also if you can see that 2 to the 2n also cancel, remaining 2 to the 2. So on top, what remains is 2n plus 1 times 2n plus 2, all divided by 2 to the 2 times n plus 1, and on the bottom, the only thing that remains is the n plus 1 term, which we can further simplify into this fraction: 2n plus 1, 2n plus 2 on the top, then 2 square, n plus 1 square on the bottom. Then we can just, the top stays the same, and on the bottom we can just factor out a square, and since this term is obviously greater than 2n, and the 2n plus 2 term is obviously greater than 2n, since plus 1 and plus 2 are just adding to 2n. Therefore, if we replace those two terms with 2n, and the bottom still stays the same, the original term should be greater than this replaced term, and this replaced term, which we can write as 2n squared over 2n plus 1 squared, which we can once again factor out the square term, the square, and what remains inside is just these two, and the 2's cancel out, and we end up with just n over n plus 1 whole square. And this is just representing the ratio If you remember, this is just representing the ratio here on top. This ratio is just p sub n plus 1 over p sub n, and we find that ratio to be greater than n plus 1 square n square. This is the relationship that we got. What this means, if we just multiply p sub n on both sides, that means n square n plus 1 square times p sub n. And since the fraction is a smaller or smaller than 1, therefore the p sub n plus 1 and the term in front is just smaller than 1. So smaller than 1 squares to some number also smaller than 1, and that means the next term p sub n plus 1 should be greater than the previous term p sub n, and we can extend this relationship to even the next term. We just add 1 to n to get this relationship, and we can extend even further to the next term. P sub n plus 2, and this continues forever. And now we see back what we want to compare our sum. What we want to sum is just p sub 1 plus p sub 2 and plus p sub 3 and so on, and using the relationship that we have just derived, that means the next term is greater than some smaller than 1 square times the previous term. Then we can just substitute 1 into n, and we get that p sub 2 is greater than the square times p sub 1. That means p sub 2 should be greater than this. Is we substitute just 1 into n, and we just get 1 plus 1 square times p sub 1. This is what you get when you substitute 1 into this equation. And also, if we substitute also 1 into this equation, what we will get is p sub 3 should be greater than the 2 square, the 2, since 1 plus 1 is 2, and we add 1 on the bottom. 1 plus 2, and whole square should be greater than p sub 2. And also, if we substitute 1 into n into this equation, what we will get is 1 plus 2 is just 3, then 1 plus 3 whole square times p sub 3. This is p sub 4 is greater than this. Then we just add back p sub 1 in front. And we remember p sub 2 is greater than this. So if we just substitute this term into p sub 2, then we should be also getting a greater than relation here, since this is the p sub 2. P sub 2 should be greater than this, and if we substitute this expression inside, then this equality also holds true. And the same goes for this. Then we substitute into p sub 3. This equality also holds true. So let us substitute that in. So p sub 1 times, with some simplification, we have 1 over 2 square p sub 1 plus simplify 2 over 3 square times, we substitute the expression on top inside p sub 2. What we will get is 1 over 2 square times p sub 1. Then we add 3 over 4 square, and we substitute the expression into p sub 3. That means we substitute the p sub 2 into p sub 3. Then we get this. And this continues. And all of this should be greater than this, since every inequalities here, every inequalities on the second step still hold true when we substitute in the expression. Now we can just simplify the expression. First thing, we may factorize the p sub 1 out in front, and we also can factor out the square inside, the square outside. So we just factor out p sub 1 and the square, and this is what we get. And now we can simplify the inside. So realize these two cancel. We will get this square, and then these two also cancel. We will get this square, and you can see the pattern continues. Well, actually here at this step we should be just simplify one step more, since the number inside is between 0 and 1, and if we square any number between 0 and 1, it should become smaller, as we can understand it by this proof here. As n is smaller than n plus 1, then we can rewrite n as n squared over n, and n plus 1 as n squared over n plus 1, and we can just rearrange the terms to end up with this expression. Then we can separate the square out to end up with this. So this is the relationship we are going to use here. So since we know that the inside number should be greater than the inside number square, since the inside number is between 0 and 1, so this is a number between 0 and 1. So the square of that number have the property of being smaller than the original, so that when we replace it, well, here actually we should try this approach. From this relation here, what we can get is p sub n plus 1 over p sub n is greater than n over n plus 1 whole square. So when we square root both sides, it removes this square. Then what we can do is just distribute the square root into the terms on the denominator and numerator, and we get this relation. Then we can move this on the right hand side to end up with p sub n plus 1 is greater than this times square root of p sub n. Then now if we compare to our sum, and let's just write our sum below. What we want to find is just p sub 1 plus p sub 2 plus p sub 3 plus so on. Then what we have found from the relationship is if we have square root of p sub 1, then according to the relation here, we can just substitute n equals 1 here. That means the next square root the next square root term, p sub 1 plus 1 should be greater than 1 over 1 plus 1 square root of p sub 1, and also substitute 2 in here. Then we get this. So now according to the relation, and we can find the square root of p sub 2 is greater than this is greater than 1 over 2 of square root of p sub 1. Then the square root of p sub 3 is greater than 2 over 3 of square root of p sub 2. And this is equal p sub 1. Then we can just add this together, and we see that the top is greater than the bottom, since everything except square root of p sub 1 is greater than the bottom. And we can continue this pattern. 3 over 4 square root of p sub 3, and this is p sub 4, and then this also continues. Then we can do the same process again. This is the p sub 2 term, which is, we can substitute this into here, and that doesn't affect our inequality. And the same for this also. We can substitute this into here. So what we will get is square root of p sub 1 plus the, if we substitute that in, we just get this, and substitute that in, we just get, substitute this term into here, we just get this, and this also continues. And now we can factorize square root of p sub 1 out, then write everything here, that left. Now we can again simplify some term or cancel some term here, here, and here, and we get square root of p sub 1, 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus, and so on. Now how can we evaluate this infinite sum? And we can evaluate this infinite sum by just comparing each term. And we realize that if we write this in full out, we can see that this 1/3 is greater than 1/2, and also 1/4 is also greater than 1/2, and actually the 1/3 should be greater than 1/4, not 1/2, and also the 1/4 should be equal to 1/4, and the 1/5 is greater than 1/4. Also the 1/6 and should be greater than 1/8, and this should be greater than 1/8. This 1/5 should be greater than 1/8, and 1/7 should be greater than 1/8. 1/8 is equal to itself. So if we just write out each term and we just group them together like this with itself, and we write the sum below, write the sum of those terms below. We have 2/4, which is equal to 1/2, and we have 4/8, which is equal to 1/2. And remember, we are summing all of those terms together of our original sum, and you can see we are comparing our original sum to the bottom sum. So our original sum on the top is greater than most of the term on the bottom sum, and if we sum what is the bottom sum, we can just write it out. We see that the bottom sum is 1/2, 1 plus 1/2 plus 1/2 plus 1/2 again and again and again, and there is no limit to how many 1/2 we are adding. So we are actually adding 1 plus infinitely many 1/2s, which is just infinite, and all of this is just infinite, and that just means our sum up here is also infinite, since we are just adding the terms together. That means this sum here is infinite, and our original sum that we want to compute, which we just compare by our bottom sum, and is greater than infinity, but we know nothing is greater than it itself. So the sum that we want to calculate actually diverges. So here, this sum is just infinity. And if we remember, we are comparing these two sums. So this is the result of the sum. This is the result of the sum here. That we just keep substituting values and factorizing and cancelling factors in order to arrive at this result. And we get that this is a divergent sum. So this is also infinite, this sum. And what we are comparing this sum to, which is greater by every term, so the total sum must also be greater. And similar case as below, only infinity itself is greater than itself. So the original sum is also diverges. But consider if you are taking a number and you square root that number, and the square root must be smaller than the original number, and we are applying this relationship here, and we can once again comparing this sum to the bottom sum. So this is also greater than the bottom sum. So we have layers of layers of layers here. We have calculated many layers of divergent sums from the bottom up in order to evaluate our original sum. So many processes have done before, and we have tried different ways to evaluate the sum. Eventually we end up with this way. And what our p sub 1, p sub 2, p sub 3 means, we just need to remember this is the p sub n means p sub n is the general term of our sequence, and we want to sum all of the term of the sequence, which we just call p sub 1, p sub 2, and p sub n, and so on. And we just through this process in order to compute this sum, which we just find out this sum is just approaching infinity. And so these two sums are the same, so that means our original sum must also diverges to infinity, as well as the sum we computed. And if I know this may be a lot of steps to follow, since I also has not tried once to solve this problem. So if you can, you may rewind the video back to where we originally started in order to review this process, as I have reviewed it many times before I record this video. So it may worth your time to see how we evaluated the sum and how the process we have done lead to our result. And I promise if it's worth my time to figure out how to evaluate the sum, and I think you will too. So remember back our topic, why we want to evaluate this sum, because the general term this represents is the probability of returning to the origin after some even number of steps, as we described it here. So we use our probability formula above to find out this sum, the general term of this sum, and then we just sum all of the even numbers, since only the even number of steps we can return to the origin. And what this means is the expected number of returns to the origin at this case is infinite. Therefore, the expected number of times we return to the origin is infinity. If we are walking randomly on a line and we expect to return our starting position infinitely many times. So that is just random walk on a line. But if you think about, we are investigating the topic of random walk as a whole, not just on a line. So we must consider not just in one dimension, but we must also consider in 2 dimensions as well. So let us now think about how we will analyze the 2-dimensional case. So in 2 dimensions, at each step we can take our step in 4 directions: up, down, left, and right. And if we continue to take steps at those 4 directions, and we will have a random walk along the 2D grid. So that is how we understand random walk in 2D. And now let's do a similar analysis as before. We want to know the expected number of returns to the origin after also some even number of steps. This time I call that 2m. This is even number of steps. So after 2m steps, we will return to the origin. So we can find this very similarly to how we do the 1D case. So we can break this expected value into, if we just see how we done the 1D case, we just remember how expected value is defined. The expected value is defined as the probability of returning to the origin times how many return it contributes. So here we can do the same. So it is equal to the probability of the number of return to probability of return to the origin after 2m steps times each return, since each return will contribute to one more return to the overall total number of return to the origin. Therefore, we times by one return by the probability of return. And now we know this is 1, and the task is to find what is the probability of return to the origin after 2m steps, even number of steps. And we can perform a similar analysis as before, as if we are returning to the origin, we must take the same number of steps to the right as to the left, to the up and as to the down. Therefore we can just draw this here: up, down, left, right. And if we have taken 2m steps to return to the origin, and if I of those steps is in the up direction, and since the only other vertical direction is down, so we must also take the same number of steps, number of steps downwards, in order to cancel out the number of steps we take upwards. And the same case as here, these two number of steps to the left should be the same as to the right. So we have a equality here. And remember, the sum or the total of the number of steps added up is 2m. So when we add up all of these steps, we get 2m steps. And if you realize the equal sign in the middle, just act like a mirror, just reflect the left to the right, and you can see the symmetry between both sides. So we can just break up the 2m steps into m steps on each side, since both sides should be equal in the same amount. So now we can find out if we take I number of steps upwards, we should take m minus I number of steps left to the left, and m minus I number of steps to the right, if we have taken total 2m number of steps in order to return to the origin. And now, how we can find out the probability of returning to the origin after 2n number of steps. And we can just if we have 2m number of steps and we just split it down in the middle, so that we have m number of steps on each side. And since we can choose any m number of steps from the 2m number of steps, so the total number of arrangements that we can choose to be m steps, we can choose any m steps inside this whole interval, and that's just correspond to the m. You can think of that each m is correspond to the m on each side. So therefore we can choose any m steps inside the 2m steps, and that is counted by 2m choose m. And that is, since after we have chosen our m steps, we can just put it in the configuration like here on both sides, and we can just match it in the same form and compare them. And comparing the number of up arrows, since we have I number of up arrows on the left within the left interval, so we can just choose any I of those to be putting the up arrows, and then that is counted by choosing I number of up arrows to put within m positions, which is counted by this term. And similarly on the other side, we can also choose m minus I right arrows to count the total number of total number of arrangements on the other side, and that is counted by m choose m minus I. And while thinking about this, you must keep in mind that the two sides, these two sides are separate, and they don't interact with each other. They just kind of just slip into each other. You can think of these two as two different layers. That just two different layers that just happens to have 2m steps in total. So they actually just don't interfere with each other. That's why when we choose the I on the left hand side, we are choosing from the first layer. We are choosing I positions to put down our up arrows, and when choosing the m minus I on the other side, we are choosing the m minus I positions to put our right arrows, and they are on different layers. So we must choose them twice, and after choosing one layer to have I number of arrows, since the total number of position is m on either side, and that means the remaining positions, m minus I positions, must be the other arrows. And also the same for this side. After we have chosen m minus I position for putting our right arrows, the remaining I arrows that is yet to be put down must have their corresponding position. So choosing one of the type of the arrows actually just fixes where the other type of arrow must put down. That's why this expression is true for counting the total number of arrangement of 2m of returning to the origin after 2m steps. So remember what we are counting here. And also the way we are counting is by breaking the 2m number of steps down into two different layers. Each layers have m number of positions, and for each m positions we just choose the I of them to put down one type of arrow, and the other m minus I positions will be the other type. And this is true for both layers, which is expressed by this term here. We are counting how many different arrangements on both layers. And now we know how to count the total number of arrangements of what we are counting. And now we try to simplify it. Let's first now think of how we can simplify this term here. Since these two terms both enforce I in their arguments, and this just corresponds to this middle section here, which has a total length of m within the interval of 2m. So therefore, another way to think of these two terms, what these two terms is counting is just choosing m positions from 2m from the interval. So you can think of combining both layers together, and these two just add up to m positions, and in total they combine to m positions, and so you are choosing m positions from the interval of 2m, and this is also what is counting on the other term. And if we multiply both of these terms, we just get 2m choose m squared, and this is our total number of arrangements on the return path to the origin after 2m number of steps. And now to find the probability, we just need to divide it by all the possible ways of arranging the arrows inside the 2m positions. Since we are working in two-dimensional, so we have two square choices on each step, which is left, right, up, and down. And since we are walking 2m steps to return to the origin, therefore, if we combine all of those 2m steps, we just need to take the power of 2 squared to 2m in order to find the total number of configurations possible of walking 2m steps to return back to the origin. And this is our probability that we are finding. Probability of return to the origin after taking 2m steps. Now we have found our probability, and we just need to calculate what is the expected number of returns to the origin. And we can do that by just once again summing up all of those probability, which is just 2m squared, 2m choose m squared divided by 2 to the 2m. So this expression, we just need to sum up this expression again in order to find what is the expected value that we are finding. And how can we sum up this sum? We may start with what we already know. And remember that we have already calculated this sum. We have already calculated this sum on the one-dimension case to be infinite. And now back to this case. Back to the 2D case. Now what we know is, let's first write out a general term, a general true 2m choose m will be always greater than 1, since we are summing from beyond 1, so it will not be equal to 1. And this is true for all m after 1. And let's multiply this 2m choose m on both sides. What we will get is this. And then we can divide both sides by 2 to the 2m. And why we divide this by 2 to the 2m? Since we know what is this equal to. This is just the same as this expression here, which you know it diverges. So what we are doing here is just making the terms that we already know of, and we are taking the sum of these terms, 2m choose m times 2m choose m all over 2 to the 2m, and that is greater than the sum 2 to the 2m, 2 choose 2m, 2 to the 2m, and this is m from 1 to infinity, m from 1 to infinity, and this sum we already know is it diverges. And what does this diverging result mean? It means the growth of the top function, this top function 2m choose m, is much faster than the growth of the function 2 choose 2 to the 2m, or 2, or just 2m choose m growing much faster than 2 to the 2m. That is what this result means, diverging result. And by interpreting what this means, and we recognize the same term on the left hand side, and we have 2m choose m term, so therefore we can just add another 2 to the 2m to recover the same term here twice. And since we know this term is diverging, and that means the top function is 2m choose m is growing much faster than the bottom function 2 to the 2m. So we can just add this 2 to the 2m, and adding this term will not change the convergence or divergence of this sum. And we already know that if we already know that if we don't count this term, this sum will greater than the right hand side, which is diverging or infinity. And if we now count this term in, we just count in this term, and by realizing this fact here, and we can just add in this term without changing the divergent properties of the original sum. So after adding this term, and which the sum just becomes 2m choose m divided by, now we have 2 to the 2m square and 2 choose m square, which we can just simplify to 2m choose m, and then 2 to the 2m whole square is greater than infinity, or diverging, that means. So now so we just back into where we are, since it can't handle this much. What we are talking is just the sum here is diverging. The sum on the left hand side is diverging. And what this sum actually is, if we just rearrange this, the above probability that we are finding, 2 to the 2m, we can just rearrange it to be in this form, which we can recognize this form is the same as this, or this sum. What this sum is actually calculating is the probability that we are finding. So as we can see, this is diverging to infinity. Therefore, our original sum is still diverging to infinity by what we have rearranged below. And this is what we are after. Hereafter, we want to find the expected number of returns in two-dimensional case after 2m steps. And through this calculation here, with this explanation, and we find that the expected number of return to the origin in the 2D case is also infinity. So that is what we have found from what we have calculated below. And what this means is if you are walking randomly on a 2D grid, maybe some path like this, so you're just walking randomly along the 4 directions that you have on 2D, and the expected number of return to the origin or your starting point is infinity. That means you will be returned to where you are started after you have walked for some time and on a plane on 2D, and assume you are walking on a grid. And if you have somebody staying at the origin waiting for you to come back home, maybe this is your mother at home and you're walking randomly on the street, and if you just walk randomly, and how can your mother be sure that you will come back home? That if she is smart, she may perform the calculation as I have done here, and so she will be sure that you will be returning home no matter how you have walked randomly along the street. And maybe if this is just for us human, so for us human, we are walking on the surface of Earth, and which we can approximate it as a grid on 2D. But humans is just one of many kinds of animal. So if other animals want to do the same, let's say there is a bird mother that is finding his or her son or daughter that was lost somewhere in the sky, and the baby bird or the baby bird may just fly randomly in order to find his or her mother or father that is finding her also. And we want to know what is the probability that they meet each other. And once they just begin their random, this is not walk but random fly. Once they begin random flying in the sky, and how likely are they to meet each other? And this is the same problem as what we have just investigated all along, but just in 3D. And in the 3D case, and we have just done 1D and 2D of what is random walk, but now we can extend it to 3D also. And if you are interested in how random walk behave in 3 dimensions, so how random walk behave in 3 dimensions, maybe you are trying to find the expected number of returns to the origin in 3 dimensions. or in 3 dimensions. This is the 3D, and then you can just start by do the same process again. Find the probability of return to origin times by 1 return each contributes. And how can you find that? And since I know this is already too involved maybe for some people, but for curious minds like me, I just want to investigate the problem deeper and deeper and deeper. Just this problem is like an ocean for me to sit down and down and down to find out how random walks behave in different dimensions. Just like what we have investigated in 1D and 2D. But now in 3D, that is where the interesting point starts. Since if you perform the same calculation in 3D, what you will get if I let you have a guess, what will you guess the expected number of return to the origin based on what we have done? For the 1D case, this expected value turns out to be infinity, and also for the 2D case is infinity. But what about the 3D case? What will you think? And I really want to show you, but since the math that gets into the 3 dimension or even higher, if you just want to extend the problem, so you can just random walk in any dimension you like, and you can just perform the calculation again and again, but starting from 3 dimensions is where the result really gets interesting. And I hope I can show you why this is interesting. But since the mathematics that involved in 3 dimensions may be not within reach of the level of education within secondary level, therefore some audience that may be studying in secondary school may not understand it that well. And I just want everyone listening to understand what I was saying, as I really like to study problems like this, and takes maybe a week to do this problem alone. But after taking such a long time on this problem, and I find it very, 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 very fascinating. And it is maybe a shame to not show what I really can do to solve this problem, because of the mathematics, the level of mathematics get involved, and maybe a little bit too little math taught in our level, and I had to research some maths at higher level, such as university. So I think maybe this discussion should be appropriate to continue when I get to university, and I think that should be the more appropriate place to discuss this problem if I am really going to look into the math of 3 dimensions and higher dimensions also. And overall, if you are not like solving maths problem like me, you may find this to be too many math involved, and if you are teaching math, then I don't know if you will enjoy solving maths problem. But as a student studying math, I really enjoy solving maths problem. That's why I take such a long time to do this presentation. Not just to show how I can solve this problem, solve it as abstract problem, and show how I progress from only basic knowledge, building up our knowledge to include more interesting subjects, and even extending to even more general problem of higher dimensions. And I also want to inspire more people like me, to take their time to really solve math problems. And because math problem really can give you that joy, and if you can't feel that joy, maybe you are just focusing on doing homework without thinking how to solve it, or how can you extend the problem from homework into more general problem. And this problem is also appear in some homework. I see some homework also ask the problem about random walk, or by walking by just through a chance or game of chance. And those homework problems can really shine a light on why I take on this challenge, to prove that I really have the mathematics foundation to do these subjects. And I just want to challenge my mathematics skills from solving challenges like this, and hoping anyone that is watching my presentation can also feel that also. And I hope if you are still listening, really take some time to investigate this problem yourself as I did myself. And I hope you can find some joy and at solving problems in mathematics, and not just doing boring homeworks, and find some joy within homework so that you can have the momentum forward to do the next question. And this is very useful when I get to university, when professors may have some research questions that they are working on, and I think this thinking skills can really benefit at the research at the university level. And if you are like math, and I hope you find what makes you like math by finding challenging problems for yourself. Maybe this is a little bit challenging for me, but I don't know if this is challenging for you, so you can try and see if math problems can really satisfy your desire to know how to solve the process of solving mathematics problems that you can not find anywhere else in problems given by teachers or schools. And also that's why I speak all of this content except mathematics, is because mathematics can really taught you how you should live on your life, as not just seeing what is obvious to you, but you also need to find out the not so obvious and trying to understand and challenging your beliefs, maybe, as what statistics is about is just use the data, not just fit by the data, understand the data, the meaning behind the data, and interpret them in the right way, and use them in the appropriate way. And also how data can change your belief about something, and you should be aware of that. And if this presentation have ever changed your thoughts on this subject, you can leave a comment, and I will surely see and reply to your comment. And I hope you have enjoyed my presentation, and I hope this is not the end of it, and I can still talk more about this problem and more in this subject. And goodbye. Thank you for your patience on listening my really long lecture.